Okay, so welcome everyone to today's webinar. It's a great pleasure for me to introduce İhsan Yanıkoğlu. So İhsan is an associate professor in the Department of Industrial Engineering at Osijek University in Turkey. And he actually joined the university right after he graduated in 2014. His PhD that he obtained in econometrics and operation research from Tilburg University in the Netherlands. And since then, he's at Osijek University. His research is on robust optimization, logistics, energy systems, and machine learning. And today he's going to talk about bilinear uncertainty. So without further ado, I want to give the control of the screen and mic to you. Yeah, Esa.
Thank you, Reza. And also thank you very much for inviting me. So today I will talk about a subject that I'm working in the last 3-4 months. So that this is still an ongoing research, and I will try to present you what I have so far. And as you have pointed out, well, the initial plan of my talk was like I want to discuss some kind of block separable bilinear uncertainty and some quadratic stuff as well. But later on, I recognize that I don't have enough time to discuss both of them. So I will just discuss the bilinear part today. But yeah, since I mean, we are in front of an robust optimization community, I just don't want to introduce what robust optimization is and so on, but still I want to give some kind of introductory information that is related to the outline of today's talk. Okay, so well, we know that the deterministic counterparts of probabilistic counterparts of deterministic constraints, we refer to them as chance constraints, so that we require this constraint to be satisfied with at least some probability, so that we, different than robust optimization, we allow some degree of infeasibility according to by having some kind of probabilistic guarantees. But what happens if we set this probability to 0? Then actually we end up with a robust reformulation, so that what you see on top and what you see at the bottom, they are equivalent to each other. So instead of satisfying this constraint for a probability distribution, we can just write that we want to satisfy this constraint for all realizations in the support of that distribution, which is denoted by U. So these two approaches are equivalent when epsilon is 0. But what happens when we select some values that are different than 0? Then we can start taking some subsets of the original support if you want to approximate chance constraint with a robust safe reformulation. So this is also kind of outline of today's talk. How we can also, this is one systematic way of selecting uncertainty sets, so that if you want to quantify how you select your uncertainty set, you can always use safe approximations of chance constraint. We know that most well-known so famous uncertainty sets like coaxial box, budget uncertainty sets are so powerful in that they can relate, they can give you some kind of probabilistic guarantees. And I will follow same line of logic in today's talk. So first of all, I just want to say the structure of my uncertainty. We assume that they are independent and taking values between -1 and 1 as in the conventional setting. You know that if they're between -1 and 1, this can be done without this loss of generality. Any parameter which has different lower and upper bounds can be scaled back to -1 and 1. And on top of that, let's also assume that they are zero mean. And I will show you when we need that, when we don't need that. But an important remark is the following: with assumption P0, we assume that our support is a box. Okay, so the original uncertainty is a box. Okay, and I believe this is most also a box uncertainty is the most honest way of talking about an uncertainty, because it's, I mean, anyone is ready to accept that an uncertain parameter lies between some lower and upper bound, at least in engineering setting where we don't have infinite bounds. So anyone is able to accept something like that because it can be easily supported by data and so on. But then when we start picking different uncertainty sets, we need much more explanation. And one way of doing that, as I said, would be safe approximations of chance constraints so that we can relate our robust information to chance constraints somehow. And when we start taking some kind of subsets, then the question is, what do we gain from the objective function by losing some degree of feasibility in the problem formulation? So that if you don't want to be robust against all uncertainties, definitely we will gain something out of objective. This is our goal. So how can we select that? Again, I will use a conventional uncertainty set like the coaxial ellipsoidal uncertainty set. Well, the power of ellipsoidal uncertainty set is, as you can see in the graph, it ignores these conservative values for the problem at hand. And more than that, it can provide you some kind of nice systematic measures how you can relate your uncertain set to, it can give you some kind of probabilistic guarantees of feasibility. Okay, so let me also repeat some kind of some results from literature, conventional results from literature. I think this is chapter 1, 2 of robust optimization book Aaron Bental. So suppose we have the base case that you see over here, and we take robust counterpart of it according to a coaxial box uncertainty set. Then robust counterpart is equivalent to what you see at 2. Okay, if it was ellipsoid, you know that if it's not coaxial box but ellipsoid, we know that it will be like the Euclidean norm of x multiplied by omega. Okay, so that then it's coaxial, but it's something close. But yeah, what you see over here, it's a second order problem, tractable. But beyond that, power of that formulation is the following. Let's pick a feasible solution out of this one. Let's pick a robust feasible solution out of this one and implement it into the chance constraint. Well, we know that this is our base case, our original constraint that is linear in this case. So that if you want this thing to be satisfied with at least probability that you see over here, now we can relate feasibility of this solution to chance constraint to the radius of the coaxial box. So that to the radius of the ellipsoid that lies inside coaxial box. Okay, so that a feasible solution for the robust counterpart is also satisfying giving you some kind of probabilistic guarantees that is determined by the radius of the ellipsoid. Okay, again, these are our assumptions that we use over here. Well, robust optimization may not, it doesn't need this zero mean assumption, but it's needed for the probabilistic guarantee. But if you want to derive your own probabilistic guarantees, the core theorem to do that is by Hofting, so that it comes out of Hofting. This is also by the result that you see before is also a byproduct of this theorem. But let me just quickly describe you this theorem, which is crucial in such kind of derivations. As you can see, SL is sum of L independent random variables, each random variables between some bounds and BI. Then Hofting theorem says that the sum of random variables minus the expected value of the sum, if it is larger than t, it is given by this expression over here. Okay, so 2 times t squared and summation of the squared sum of the basically the length of the range of the uncertain parameters, and you take their squares and take the sum. Okay, so let's look at, and the crucial part of this theorem comes out of this. As I said, it boils down to checking what is probability of having the left-hand side of the uncertain constraint larger than the robust counterpart of the same constraint with respect to an ellipsoid, so that when my left-hand side could be larger than my robust counterpart with respect to an ellipsoid, what's probability of that is equivalent to that one. As you can see now, xi's that you see, xi's over here are like xi multiplied by xi I. Xi i's are between -1 and 1. So that xi becomes a random variable. that is between an upper bound xi and minus xi. So that returning back to this definition, we have sum of L independent variables which has bounds minus xi and plus xi. Okay. Well, when I say minus xi and plus xi, I'm referring to small letters. Okay. So actually, this part becomes like 2 times xi square. When we take a square, 4 times xi square, we take 4 multiplied by sum of xi squares. As you can see, my t is this one. Well, I don't have any expected term because the expectation of that one is 0. Expectation of the sum is 0 because zetas are 0 mean. So that 2 times this guy, 2 times omega square, sum of xi squares, divided by 4 times sum of xi squared, they cancel out each other and we have this result. Okay, so well, this is where this result comes from. Okay, so that you can see it's also a nice way of seeing left-hand side of the uncertainty set will be larger than its robust counterpart with respect to an ellipsoid when the original support is a box is less than this probability. So that this is you will definitely gain something in the objective. This is what you will lose in the feasibility, and it has some kind of probabilistic guarantee. For example, if you set this omega value to 2, it is around, I think, 95% or something like that. Okay, so that I mean, if you allow some degree of infeasibility, then you will definitely gain something out in something in the objective. So I will follow the same line of logic in today's talk. So, but I don't have linear uncertain optimization problem, but I have some setting that you see over here where we have block separable bilinear terms. And this could be, I will also discuss some applications in the last part of my talk. So, but let's first focus on the technical part. So this is the general setting, and I mean I just keep it general. You can set any structure for this AX, WIX, so that these are just vector decision vector functions. And we have some bilinear terms. And since they are block separable, what do I mean by block separability? So that 2 different blocks, they don't share the common indices in the variables. This is why I can order them like 1, 2, 2, 3, 2, 4, 5, 1, 2, 3, 4, 6, 5, 6, and so on, without loss of generality. And I just do it like that for the sake of simplicity in the notation. So I'm trying to take robust counterpart of such a constraint over an coaxial box. Again, like in the primary assumption, I assume that the original support of these uncertainty parameters are between -1 and 1. And I will just try to find some kind of robust counterpart of this problem with respect to coaxial box. And I will try to follow the same line of logic. Can I provide some kind of probability bounds for that, and so on. So we can translate the semi-infinite problem to a nested form so that we can maximize this part, which is the part that only contains uncertain terms. We can ignore the rest, deterministic part. So I'm interested in maximizing this over a coaxial box. Well, we have discussed already what coaxial box is, and my strategy to do that would be the following. First, I will substitute an auxiliary uncertainty auxiliary variable that resembles that's equivalent to this bilinear terms. Like for this one, I will say psi I for block I. I will just substitute it to here. Then I will have some kind of bilinear terms in my constraints. And after that lifting, I will convexify these bilinear terms using McCormick envelopes. And then I will try to derive some kind of derive the tractable conic robust counterpart. But this convexification is outer approximation. So I will then try to strengthen that one a little bit further in the second part. Okay, so let's start with this line of logic. The first step is lifting the bilinear terms so that we introduce psi I for each block. Sometimes I also denote these blocks with this vector, so that if you see some brackets like I, it is a vector of this in the given block. Okay, so that if you see some kind of brackets like that, means what you see on the right hand side. So when we lift that, we have something like this. And as I said before, now I translate that bilinear term to my to the definition of my uncertainty set. What you see here is coaxial box, and now I have these bilinear terms like some bilinear manifolds over here. Okay, so as I said before, well, we know that we can find robust counterpart of this problem if we take convex hull of this uncertainty set, okay? So that because our objective is linear in terms of the uncertainty parameters, if this part is non-convex, we can always take convex hull of it, okay? But this is not that trivial. So I just started the following. Instead of taking the convex hull from the outset, so that also including the ellipsoid term, I just take convex hull of this part, okay, using McCormick relaxations. And as I said, when I do that, this is not the convex hull, but outer approximation of the convex hull, meaning that we will have some kind of conservative, robust reformulations of the problem. Okay, so I think we are familiar with McCormick. It was an exact reformulation of this problem if this ellipsoidal constraint was not there, by the way. Okay, so if it was like the regular box, it was exact. But now, because of this inclusion, it becomes an outer approximation. Okay, so that my uncertain set is something like as follows. So that I will keep it like this, and I will substitute McCormick inequalities for this part. Okay, I want to put a remark on that once more. Since each bilinear interaction is convex independently, before introducing a global ellipsoidal coupling, it follows directly that convex hull of the original uncertainty is what we propose over here is outer approximation of the original convex hull. Well, it is easy to see that why it is outer approximation. So I just dumped everything in the formulation to here. This is my uncertainty set. This is the constraint. So suppose you use the Euclidean budget with omega parameters. Rest of the parameters are zero, okay? Suppose I pick omega parameters and randomly pick omega parameters and set their values to 1, then it means that I have used my budget for the ellipsoid. Rest of the parameters will be 0, okay? Let's consider these parameters which are 0 for each. And suppose they're also some of the blocks I have. Put 0 here, and you will see that this puts some kind of loose bound on psi I that says it is between -1 and 1 when both of these parameters are 0. 0, 0, it says psi is larger than -1. It says psi I is smaller than 1. So that returning back to the maximization for the terms which are 0, 0, I can still pick independently values of zeta to -1 and 1. This doesn't avoid that. So that this formulation doesn't avoid that. I can still pick some zeta I values to -1 and 1 when they're corresponding, psi I values to -1 and 1 when their corresponding zeta values are 0. This is why it is a little bit conservative, okay? It tackles the ellipsoidal structure, but it is not so good for modeling. This part is relatively more conservative than this guy over here. Okay, but still check it. So this is the conic representation. I can represent McCormick inequalities as I have shown here for each block. Each block I can write it like that. And then the general McCormick can be written in this form. Okay, this is my ellipsoid, so that I will try to maximize left-hand side of this constraint under these conic constraints. Okay, so that I take the conic dual and ended up with a formulation that admits the following tractable robust counterpart, where Z here denotes the dual vector for McCormick inequalities, V denotes dual vectors for the ellipsoidal constraint, and this problem can be solved. It's a tractable class. Of course, I know that the original problem can contain some kind of challenges if these vectors are challenging, but suppose they are tractable, then we do not introduce additional level of complexity to the existing problem with this formulation. Okay, because SOCP is a nice class. Okay, so if you remember now, I just want to relate my coaxial box to chance constraint somehow. So that suppose you take a feasible solution out of this guy and implement it into the chance constraint. Can I still provide some kind of probabilistic guarantee? Well, I have seen that. Well, it is not so, I do not provide here the formal proof, but it is not so, I can give you the intuition. As you can see, we have the same bound with the original case, which is coaxial box. For the linear case, we have the same bound. If you remember, I have shown you that. Now we also have the same bound. And as I said, I can give you the formal proof, but intuition is so clear. Since we cannot reformulate, we cannot relate zeta terms to psi in the best way. They take their worst case realizations independently. Psi's can take their worst case values independently so that they're unaffected by the ellipsoid. The only part that I'm affecting is zetas, and zetas resides in some kind of ellipsoid, but psi's are independent, taking -1 and 1, so that they are fully robust. But psi's are, zetas are in the ellipsoid. Well, this is nothing different than the original formulation. I just guarantee that zetas are in the ellipsoid. And well, if you are interested, proof comes in the end, something like this. Okay, so you ended up with some term like this, and we know from literature that this has such a guarantee, and then for this case it also holds. Okay, so now the thing is, I have a conservative approximation, but for that solution I can provide you some kind of probabilistic guarantees based on Hofting type concentration bounds, so that a feasible solution for our coaxial box calibrates with the radius of the ellipsoid. Okay, but as I said, this is a conservative approximation. Can I find something better than this? So main issue, if you remember before, was like put zeta to I minus 1 to 0, like pick two pairs, zeta 3, zeta 4, make both of them 0, then psi can take value -1 and 1 because I do not bound it. Okay, now I've tried to introduce some kind of valid inequalities that bounds this. Okay, so I introduce a new variable, which is an upper bound for zeta I square. Basically here, we know that psi I is multiplication of zeta 2i minus 1 and zeta 2i. And if you take it square, psi I square of these bilinear terms, okay? So basically, I'm just introducing some kind of valid inequalities from here. As you can see, this upper bound for this guy. And if you substitute this guy to here, you will see that this is another upper bound, valid upper bound for psi I, because psi I square is equivalent to squares of the bilinear terms. Okay? And I introduce my ellipsoidal constraint and I sub like this, and I substitute with this one, okay? So before, with McCormick inequalities, we can tackle the bilinear manifolds in a good way, but we cannot relate it to ellipsoid, okay? Now what I'm trying to do is, can I reformulate this ellipsoidal part better or not, okay? So this is what I'm trying. So I introduce these three set of constraints to handle this, okay? And each of these guys has a very nice second order representations, okay? So in the end, we have something like this. And for this case, if we return back to this original result, suppose again I use omega budget in omega parameters, rest of the parameters, suppose the rest of the zetas are 0, then this constraint will tell you that zetas are 0. Since my budget is used, all the parameters that are not selected as 1 or -1 will have a tau value equal to 0, okay? So that for all of these parameters which has a tau value equal to 0, this constraint basically says the following. If these two taus are 0, then your psi I must be 0, which was not the case before, okay? So that, pick again, as I said, omega blocks, omega parameters, and set them into their worst case values, okay? So that I will use my budget fully. And then for rest of the parameters, taus can be nothing but 0 because this is binding in this case. When they are 0, now I bound the value of psi I to 0, unlike before, okay? Before I cannot do that. So now my uncertainty set is something like as follows. The three constraints that I have introduced plus the McCormick constraints, okay? This is my, I denote being tighter with this tilde. This is my new uncertainty set. And again, I want to take robust counterpart of the problem, the same problem with respect to this new revised uncertainty set. Well, we basically adopt the same 4-step procedure. We lifted it, convexify it, then use duality. It was maximization. Then we take dual, it becomes minimization. We delete minimization and obtain the final formulation. It is something like this. I know that it looks a bit ugly, hard to follow in this case, but yeah, I also provided you the explicit form. Hopefully, there are no plus or minus mistakes in this formulation. We tested it a little bit; it works, but still, that it's prone to some kind of plus and minus mistakes. But I think it's correct. Okay, so yeah, the final RC is something like this, and well, it's also again some kind of nice structure here. These two variables are again lying in it's a conic formulation. They lie in Euclidean codes, okay, Lorentz codes. Okay. Can I also find, suppose I pick a feasible solution out of this guy and implement it into chance constraint, can I find some kind of probabilistic guarantee for this solution? That is as a function of my core parameters radius of the ellipsoid. So can I find some kind of relationship between the probability and omega, basically? Okay, so that for this one, I don't have, even though my formulation is better, now I cannot find a bound that's as good as before, but it's still okay. But its derivation is kind of different than the original logic. The original logic exploits the structure of the robust counterpart. This one is more general. So since I have derived the robust counterpart, all my solutions are robust. We are 100% sure that all my solutions are robust to the coaxial box. We are even more sure, more robust than that because we take outer approximation of that robust counterpart. But what we cannot be sure is the following. If this data lies outside the ellipsoid, then I cannot guarantee you that I'm robust against that, okay? So therefore, here I just provide a bound that says, what is probability of zeta square larger than this guy, meaning that what's probability of zeta is outside the ellipsoid, okay? When it is also bounded between -1 and 1. This is basically, these are the realizations that I am not 100% robust against, okay? I cannot give you a guarantee. Maybe I'm extra robust, but I cannot give you any guarantee. Again, out of Hofting theorem, we can show you that, I can show you that this probability is equivalent to what you see over here. So that this is the probability of being infeasible if you use the solution of the robust counterpart. Here there is a small typo. It's, I mean, this sigma I, there's sigma square, this must be sigma I. Okay, it shouldn't be square. It's not square of that. It's just sigma high, sigma I. As you can see here, different than the previous conventional result, we require additional information. So that before we don't need that, now we need it. Okay. So if it is zero mean, this is basically the variance of the ith parameter. Okay. So that inside this bound exploits information, additional information. If we have assumption P, which means that if we have zero means, then it's equal to variance. The formulation RCB tilde is tighter than the previous formulation, but I cannot guarantee you that it will give you a better solution for the same probabilistic guarantee, because its probability bound is looser than the previous one. Okay, but I will show you some examples. And as I said, you can use this bound for any setting. Namely, if you are taking robust counterpart for coaxial box, any RC satisfy that property. It is not exploiting the structure of robust counterpart, because it's just saying, if my uncertainty lies outside the coaxial box, what's probability of that? Okay, so since you are not robust against that, well, this can be a bound for your solution. Okay, since the result is so general, of course, we expect that it may not be that strong, but we will see some examples. Summary. So both formulations are tractable, second order Cohen problems. Coaxial box is more progressive than standard box. We will gain something in the objective function value, definitely. Provides analytical probability guarantees using Hofting and the conventional results, and it's flexible, so that depending on the tractability of the original problem, it can be integrated into larger instances. Okay. Before discussing some examples, let me give you last final formulation. Of course, we discuss coaxial box, but what happens? How can we take robust counterpart with respect to box? Since it is more trivial, I will not discuss it with the same level of information, because now we remove that ellipsoidal constraint. Now McCormick becomes exact. You will adopt the same procedure. You will lift it, convexify it with McCormick, derive robust counterpart, and obtain what you see over here. So that this is the original full robust counterpart for all realizations of the uncertainty. We will use it as a benchmark for the worst case guarantee. It ensures worst case guarantee. We will use it as a baseline for our solutions. So that what do we gain in the objective function value if we lose being full robust? So that what happens if you use coaxial box? What do we gain in the objective function value? It will be our base benchmark. Well, it's just omitting the ellipsoidal constraint from the previous formulations and adapting the same logic as I said. And this formulation is exact because McCormick, when there is no ellipsoidal requirement, it is exactly representing the convex hull of bilinear manifolds. So that, and the final robust counterpart is something like as the one that you see over here, adapting the same notation. Okay, and this will be our benchmark. Okay, so we discussed a lot of theory, and it gets boring after some point. So let's discuss some applications, because I think the first time I worked on this subject was second or third year of my PhD. Okay, so I mean, up to some time I couldn't find very nice application, but later in 2022 and 2023 we see some kind of real applications where we can apply this, because well, the theory is there, but if there is no real life application, it's not so interesting for my side. So now I will show you what kind of applications we have, but before we start on intuition behind real life applications, I just want to discuss an illustrative example. Okay, so suppose a portfolio selection problem. Reza, how many minutes do I have?
I would say 15 minutes.
Okay, nice. Yeah, I have enough time. Okay, to discuss the rest. Okay, so the problem definition is just we just select some set of options. Suppose there are n potential investments, and the goal is to maximize total expected return subject to a risk-weighted capital constraint. I know that this example is not out of transportation logistics, but I will return back. Okay, so just an illustrative example, and I just want to create story behind this example, even though I don't need one. But I mean, why not if we have such kind of story? It's nice always. Okay, so expected return is determined by V, cost of option determined by C, risk of that option determined by R. So suppose we have some kind of total risk-weighted budget capital W. So if I invest on option I, it is a binary variable 0, 1, okay? So my problem is something like as follows. So that risk of option I, cost of option I, if I select, I use my space in my knapsack, equivalent to that one. This is the capacity that I cannot exceed. And I want to maximize my returns, okay? As you can see, these risk I's, and suppose this risk I's and risks and costs are uncertain. This is sum of binary terms, and they are block separable. Okay. Parameter intervals, suppose they are between some lower and upper bounds with some kind of affine transformation like I have described before. I can scale them between -1, 1, and 1 using such kind of logic without loss of generality, which corresponds to primitive uncertainty. Okay, zetas are primitive uncertain parameters. And well, I don't need to assume some kind of distribution, but I just want to materialize it. I just want to give you some kind of concrete example. I know that it is not so reasonable to assume all of them are following the same distribution. We can change it, but at the end of the day, I only need their variances. But I just like suppose the variance is 1 divided by 15, something like that. And I just show you only one class that satisfy that property. Zero mean, variance, 1 divided by 15, and between -1 and 1. I suppose all of my parameters are having such kind of variance. This is only one class that satisfies this property. There could be several other classes, like there could be a class of triangular distributions and so on that satisfies the same property. Okay, but I just want to materialize that, and also we know that I mean it is quite challenging if you want to adopt a chance constraint for the product of truncated normal distributions. I mean, I don't know how to write the PDF, so therefore this is why I also pick such an example just to show power of robust optimization, kind of. Because the explicit formulation, if you want to go standard chance constraint approach, I think it's not that trivial if you want something exact, of course. So the values of the options, returns of the options are provided over there. They are expected returns. I don't provide any uncertainty on that since it will not change anything. It will not give us extra. I mean, we can have uncertainty in the values, but it can also be formulated. But here they are deterministic. Cost on bounds, I provide nominal values on the left-hand side, and we just lower and upper bounds are like 15% plus and 15% minus, okay? Risks are given as follows. And our risk-weighted budget is 1,800. And I compare the 5 formulations. And target reliability, we want some kind of, we want an investment that will exceed this budget at most 10% of the time, okay? So if this experiment is repeated, well, our risk is we can exceed that weighted budget at most 10%. So for the given reliability, the first reduce the standard coaxial box, our first formulation doesn't require any variance information. For this reliability, 90% reliability, omega 1 is this value. Our tighter reformulation that use the second corollary for finding bounds, when the variance is that one, its corresponding radius is 2.01. Well, here we use the variance information. And I just want to emphasize that in this case, the omega of the title reformulation is smaller than the standard formulation, but this shouldn't be the case 100% of the time. Okay, there could also be cases, especially if you increase the dimension. It is very likely that the omega values for the second reformulation will be higher than the first one, because it is not as tight as the first one, and it requires variance information that affects the behavior of the exponential function a lot. Okay, but in this case, for the given parameter values, it is like this. Okay, but as I said, for the tight reformation, the bond can be the omega value can be larger, smaller. It depends on what bond you have, what data you have, amount of uncertainty, number of uncertainty parameters, variance, and so on. Okay, these values can change. At the end of the day, what I can tell you is the following: I'm 100% sure that both solutions will guarantee the same reliability using the robust counterparts that we have derived. Okay, so then we solve this problem. Of course, it is not so nice to compare deterministic solution, but still there is something nice in this hypothetical example. I mean, let's first look at full box and deterministic, so that when you want to be robust against uncertainty, you lose something in the objective function value, definitely. But what is so fun in this setting is the following: our deterministic model is kind of robust as well. Okay, so it is kind of robust as well. For example, if you compare deterministic model's objective function value, it's also robust against 10% reliability, not 100%. It cannot be robust for 100%, because as we can see from here, robust cannot satisfy that. But if you give me some kind of, some flexibility for being infeasible for the weighted budget 10% of the time, then as you can see, it is kind of robust. However, our conservative reformulation cannot find that solution. Okay, because it is being too conservative, it cannot find this solution. And it ended up with the solution of fully robust one, which is investing in 1, 3, and 5. While the tight reformulation in this case can improve the coaxial box that is solely dependent on McCormick reformulation. The tight one is, as you can see, better. In this case, what is extra is the following: our deterministic solution is kind of robust. Okay, so but the core message is the following: as you can see for the specific illustrative example, the tight reformulation recovers the improved objective. Okay, so it performs better than coaxial box, the conservative one, and it improves the fully robust counterpart around more than 20%. Okay, and so that with 10% reliability, I can gain 20% in the objective. Okay, if you are okay with that, you can go with that solution. So the last part of my talk, I will just try to give some kind of intuition in last 5-10 minutes. I will talk about how we can relate this thing to some kind of more realistic problems in the domain of logistics. Okay, so and this is how we come up with some ideas of having separable bilinear terms, separable and quadratic terms, and so on in our previous applications. Okay, so I will try to give you some kind of intuition when we have such kind of setting. So, and all of these works were in the domain of using electrical powered vehicles in a logistics setting. And the core constraint in our former research was something like as follows. Okay, so that in each of these EV-based research, you have some kind of battery constraint. So that suppose you pick the schedule routing of a specific vehicle K. What you want is the following: you don't want to exceed the capacity of the battery in your trip. Okay, So that this is the total trip of a vehicle. When you take the summation xijk denotes if I go from node I to node j, or it can also be trip, so that each trip has some set of predetermined segments, and you decide which trips, the trip schedules. Basically, this is also a routing decision, how you would order trips. So this is one if I go from node I to node j, if I go from trip I to trip j, and k is the index of vehicle. Therefore, this denotes the total consumption of car in a given route, okay? And we cannot exceed the battery capacity. In the first research, we focus on such kind of uncertainty was there, but they don't allow us to change the routing. So they requested from us to install dynamic wireless charging stations on road, so that it has also different structure. Here you can at the same time charge the cars while they are traveling, so that you can have some kind of minus terms over here if you charge them while they are traveling. Okay. So in the second one, we decide on robust schedules of buses. Okay, robust schedule of buses, and each of these problems, of course, there were several other constraints, but the critical constraint that follows the structure that I will discuss right now is this battery consumption constraint that includes some kind of nonlinear terms that are similar to what I have presented today, okay? So let's delve into details of this TIJK a little bit more. Okay, so this is the battery consumption formula that is quite often used in literature also. I think it has some kind of engineering background, so that this is used often in the literature, where the first part determines the aerodynamics of the car, second was the rolling resistance, and third one is the slope resistance, and last term is the accessory related consumption, like heating, ventilation, lighting of the car, and so on. Okay, so that here the total consumption is affected by two uncertain parameters. Well, the travel time is one of them, Pij. Suppose it lies in some interval, again with some kind of certain lower and upper bounds, like we have shown, like a box as we have discussed before. And the second parameter is the payload of the car between trips. Okay, they are also changing and uncertain. And when we look up this formula, when we play with it a little bit, we see that it starts containing some kind of bilinear terms, like the ones that you see over here. So that it has some kind of linear relationship as well as some kind of bilinear terms. And each term is associated with a specific arc. And a tour of a car is summation of these arcs. So that at the end of the day, we have sum of bilinear terms in this constraint because of the structure of consumption of the car presented over here. Okay, but we need to be careful. I will discuss this formula a little bit further, so that, as I said, here in this case, in this parameter, we have some uncertain parameters that comes out of this formula. Okay, and the original formula is something like this that comes out of this formula. And the robust information of the uncertain equality that I have discussed today is flexible enough to cover that case. Okay, and well, here in this case, VIX is like XI, and maybe we don't have some of the terms over here, but this is generic enough to reformulate battery constraints, so that we can use the terminology that we have discussed today to formulate such kind of constraints. But we need to be careful because yeah, I just want to discuss something out of this formula. Each case can correspond to different robust reformulation. Okay, so the as you can see, Vij is velocity of the car, Tij is time it takes to travel that arc. Okay, And here I put some kind of star into last Tij. These are essentially different than each other, and I just want to discuss it. Okay. So even though depending on the application at hand, they can have different meanings. So coupling of time, distance, and speed. So distance, this part is distance, Vij, Tij is length of that arc. Distance, Lij, travel time, Tij, speed, Vij are not independent. So that how we model uncertainty depends on the structure of the segment going from I to J, okay? If you are talking about fixed lines, like in bus networks, going from I to J is predetermined. It's not subject to change with a huge deviation. But it can also effectively be variable, like in the transportation of like line haul transportation, drones, marine transportation, going from I to J, not necessarily have a fixed length, okay? So that we have two cases, logistic cases. Suppose first Lij is fixed, okay? So that you are designing a bus network from station 1 to station 2, route is given to you and it is fixed, okay? So it doesn't change in such kind of application. If this is the case, when Lij, when the length is fixed, so I just substitute Lij over here as you have seen. Lij is given by the network geometry, so that is fixed. What we have is nothing, it is not bilinear anymore, so that aerodynamics is affected by Vij square, rolling is affected by payload, slope is affected linearly by V. And here, well, the propulsion, the driving time and the total time it takes going from I to J are two different things. Because the second Tij in an electric bus setting, in a bus network, going from station 1 to station 2, if they have some kind of robust schedules, doesn't change much, but bus arrives earlier and waits there. So that the accessory consumption is kind of fixed. While the time it takes to for propulsion, regular transportation, may be different, okay? Therefore, in such kind of settings, if we are looking for some kind of electric bus EV settings where the routes Lij is fixed basically, we can assume that that part is determined and it is fixed. And the rest of the structure is something like as follows. As I said, this function is not bilinear. It is subject to uncertainty in the velocity and the mass. Well, today, since I don't have enough time, I couldn't discuss this case, but I also have some kind of robust reformations for this case as well. Okay, but I haven't discussed that. So I have described all the required information that are listed in these three items. Remark, this is quadratic, not linear. It was not today's subject. Let's look at case 2. Flexible link applications, namely Lij is subject to change. Okay, when is Lij is subject to change? Like in last mile delivery, line haul transportation, we can assume that Lij is variable. And we can even assume that velocity of the car is variable, but the time is changing because of the changing in the path. Okay. So if you are in this case, then we can assume that M and Tij are uncertain, so that the vehicle carries an uncertain payload over an uncertain duration of time. And when we are in this case, then the rolling resistance scales with the bilinear term. Auxiliary consumption, which was ineffective in the previous formulation, now it can become effective because now we don't have predetermined schedules. Tij is also effective in the consumption of the accessories of the car. Before it, we can assume it in other applications, we can assume it fixed, but in this case, it's affected by Tij. Aerodynamics is affected by also Tij, assuming that Vij is fixed. And it's quite often an assumption that is made in such kind of applications like line haul transportation. And in such kind of setting, when Lij is not fixed, but it is variable, this nature leads to bilinear and linear dependencies of consumption, linear dependence of Tij and Mij. which is corresponding to the case that I have discussed today. And our robust deformation is designed to capture such kind of interactions. Okay. As I said, since I don't have that much time, I haven't discussed this case, but in electromobility, in some kind of applications, we have the quadratic terms. In another set of applications, we have bilinear terms, so that, and when we cover both of the formulations, we have some theory and application domain for the associated robust optimization setting. And this concludes my talk for today. So what I have done is, like, I just linked again, very, very conventional, but I linked chance-constrained to robust optimization and provide some kind of probabilistic guarantees for robust solutions, and develop some kind of second-order problems that are tractable, given that the original problem is, I mean, it's best to say is the following: we do not introduce an additional level of significant complexity to the original problem. Of course, we can make a linear problem, a non-linear problem, but still, I consider SOCP as a tractable class. Our technique is we just use lifting, relaxation, and then conic reformulations. We provided distribution-free probabilistic guarantees using opting type of bounds. Sometimes we require some additional information like variance and so on. And I illustrated you a simple example, and I also show you some kind of roadmap how we can apply this methodology in a logistic setting. And this is all I want to say about for today. Okay, thank you very much for listening.